All right, welcome back. We are still talking about event studies. And in this video in particular, I'm going to talk about something called an interrupted time series approach to event studies. Now, we have this idea of event studies. We see some sort of trend beforehand, an event occurs, and then we see some deviation between what we would predict and what we actually observe in the after treatment period. And we want to know, well, what's the effect of treatment comparing what we saw to what we predicted we would see? The big question there is, how do you create that prediction? So there are a number of different ways that you can create that prediction, but probably the simplest way is the interrupted time series. And this is a good method to use if you think that there's likely to be some sort of consistent trend over time, and then maybe another consistent trend afterwards, and just you're interested in the difference between the two trends that you see. So what interrupted time series is this. You first fit a time trend, perhaps using regression, in the pre-treatment period. Then you fit a time trend using perhaps regression in the post-treatment period, and then you look at them and you see where those trends meet up. So this trend that you might see, maybe you have a declining trend beforehand, and it seems like it's going down, and then you have this trend that you fit afterwards, and it seems to start right up here. It looks like there's a jump right there. I predicted that we would have continued the trend and gone down here, and yet we ended up here, right? That is an interrupted time series. You see a time series, a time trend that's going along, and then the event occurs, and we interrupt it, and it moves on to something else. This is, by the way, at least mathematically, quite similar to the concept of a regression discontinuity design, which is something that we will address in a few chapters from now. So implementing interrupted time series is as simple as that. We simply need to estimate a time trend using before treatment data and estimate a time trend using after treatment data, and then see where they line up at the point where the treatment goes into effect. What is the jump there? Now, there are many ways to do this. You could use advanced time series methodology to make some sort of forecast, and it's probably honestly better if you do. But a simpler way to do this is to simply use linear regression with an interaction term. Interaction terms are great. So you can estimate an interrupted time series as simply as this equation right here. We take our outcome, we regress it on time, so some sort of continuous measure of time, maybe the week or the year in which the observation is made. We also have a term, a binary indicator for being after treatment. So either you are in the before treatment period and untreated, or in the after treatment period and treated. And then we have the interaction between those two things. And that is it, at least if we're willing to make a slight adjustment here. If we take that time variable and we subtract the cutoff date from it, such that the time variable is 0 at the point where the event goes into place, then the interpretation of this model is very straightforward. The line in the untreated period has an intercept of beta 0 and a slope of beta 1, right? You're in the untreated period, so after is equal to 0. The beta 2 term falls away, the beta 3 term falls away. We are left only with beta 0 plus beta 1 times t. That is our line in the pre-treatment period. How about in the post-treatment period? Well, in the post-treatment period, after is equal to 1. So our intercept is beta 0 plus beta 2, and our slope is beta 1 plus beta 3. Now, the thing we are particularly interested in most studies is how things jumped at the cutoff. How did things jump at the immediate point when treatment went into effect, going from the untreated to the treated? If we saw that trend line using beta 0 plus beta 1 t going along, we hit our intercept, and we should see a jump if there's some sort of immediate effect of treatment. Well, the intercept is the predicted value at 0, and since we just centered our time variable so that 0 is at the event date, then we are simply looking for the change in the prediction at 0, which is the change in the intercept, because the intercept gives us our prediction at an x-axis value of 0. So we simply compare our intercept in the untreated period, which is beta 0, against our intercept in the treated period, which is beta 0 plus beta 1, to get the effect of treatment. So the beta 1, which is the jump in the intercept, is going to be our treatment effect of interest. So we are looking for the jump at the treatment point. And since we just centered the time variable so that a value of 0 is at the event date, this makes things very, very simple. Because what is happening at 0? Well, our prediction at 0, our prediction at an x-axis value of 0, a time of 0, is the intercept, right? If you set all the variables to 0, if you set time equal to 0, after equal to 0, then you're looking at the intercept right there, which is beta 0. And if we're looking at the treated period, well then time is still 0, but after is equal to 1. So we're looking at beta 0 plus beta 2. So the difference between those two intercepts, the jump at the intercept, which is the jump at a value of 0, is the event study effect of interest. So that goes from beta 0 to beta 0 plus beta 2, and therefore we see a jump of beta 2. Beta 2 is our effect of interest as estimated with the interrupted time series. Let's see a quick example of this. So this is from a study that looked at a quality improvement program for ambulances. So they took a way of making ambulances coordinate information better, and they wanted to know, hey, does it make things a little bit more effective in terms of the performance of those ambulances? The treatment was put into place at a particular time, and we want to know what changes about the effectiveness rating of those ambulances. So what do we see? Graphically, we can very easily fit a straight line on either side of the cutoff. So you can see that to the left of the cutoff here in the untreated period, we have a straight line that's sloping upwards slightly, but only a little bit. And then we get to our cutoff period, and then we estimate an entirely separate line on the right of the cutoff in the post-treatment period. So we don't really see any sort of jump in the prediction at the treatment point, which suggests that there is not really at least an immediate effect of the policy going into place. However, we do see that the slope gets steeper at this point, suggesting that maybe we can use this to say that there wasn't any immediate effect, but maybe this quality improvement program seemed to make things better over time slowly. So a couple of brief notes about doing interrupted time series. The first is that you don't necessarily have to make it just a straight line. You can add things like polynomials pretty easily. You just add an interaction term between your after indicator and all the polynomial terms that you add, which will allow you to do things like have non-straight lines, which you might have in your data. The other thing to keep in mind is that doing the standard errors is a little bit difficult because you're likely to have autocorrelation in your error term. If you look back at the regression chapter, you can see some stuff about autocorrelation in the error term. So you're going to want to keep that in mind as you estimate things and estimate your standard errors. If you try to do your interrupted time series with just a regular regression without any sort of bells and whistles, without any sort of adjustment for autocorrelation, without a recognition of the fact that an observation in one period is likely to be correlated to the observation in the next period, you tend to over-reject the null. That is, you're likely to say that you've found effects when you have not, in fact, found anything at all, which is not good. So that's an obvious downside of the interrupted time series approach. It is very sensitive to the choice of functional form. So it's not just, willy-nilly whether you choose a linear form or a polynomial or whatever. It actually has very big implications for what kind of effect you see, because the shape of the curve is going to be it's going to make its weirdest prediction sort of near the edge, right? A straight line might predict up here, but a curved line, when you make that curve, it doesn't really change that much in here, but it changes a lot over here, right? And that's what we're doing, right? We're looking at the edge of the line right at the point where the event goes into effect. So you got to be really careful about your functional form, and you also have to be really careful about the presence of autocorrelation, which you almost certainly have in this application. All right, so that is one way to apply event study methodology, is to use an interrupted time series, where you fit one time trend on one side of the data in the pre-treatment period, one time trend in the post-treatment data, and you see where they line up at the point where treatment occurs. Do you see a jump in what you observe at that point? That suggests that the post-treatment period is above where you would expect it to be based on the prior time trend. That's it for this video. In the next video, we're going to talk about some different ways of applying event study design and estimating them. Thank you.